there's four basic things that we need to consider when we look at NMR, okay? So I'm going to summarize them, and then I'm going to go back and hit each of those in a section. And I'm not going to try to drag this out too much, but I just want to make sure we're on the same page, because these are the four things that you need to know if you're not going to go on in chemistry. Okay? So in other words, if you go in to take the MCAT does have NMR on it. If you take the MCAT and you see NMR questions, they will basically be from these areas. Okay? That's it. So the advanced stuff that I teach you tomorrow would not be on the MCAT, in my opinion. All right? Okay, so let's look at these areas. So the first one is equivalence. Equivalent atoms, okay? The second one is integration. The third one is chemical shift. And the fourth one is splitting. Okay? And tomorrow, we're going to look at these areas again in a little more detail. So there's a basic level of understanding, which will get you through probably 90% of everything you ever needed to know about NMR. And then there's advanced stuff that if you were a chemist or doing organic chemistry or whatever, you would need to know this additional stuff. Okay, so we'll cover the advanced stuff tomorrow. For today, we're just going to hit this on a very straightforward level. Okay, so first of all, atom equivalence. Now, we're going to focus on hydrogen equivalence, but effectively, atom equivalence is a general property of atoms that are covalently bonded in a molecule. So when we do carbon NMR, we talk about equivalent carbons. We're going to do hydrogen NMR, what we call proton NMR, talk about equivalent hydrogens, okay? All right, so first of all, a definition, okay? It's a wordy definition, okay? So blah, 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 blah. And you guys don't have to jot this down if you don't want to, you can. I am going to post these notes. But basically, here's the concept. We have a molecule, it's got carbon and hydrogen bonds in it. So we say, here's a hydrogen. What if I replace that hydrogen with some group X? Okay? Now I look at another hydrogen. What if I, instead of replacing the first hydrogen, I replace the second hydrogen with X? So when I replace the first hydrogen with X, I get a new structure. When I replace the second hydrogen with X, I get a new structure. Right? So I've replaced each of them one at a time and then put it back to a hydrogen after I did, right? Then I compare the two structures, or maybe there's more structures, and I say, are they identical? Right? And comparing structures, it was a skill that we talked about very early last semester. We started with constitutional isomerism, right? To have the same connectivity, but then we looked at stereoisomers. And it turns out that if they're stereoisomers, if they're constitutional isomers, there's a good chance they're not equivalent. There's one exception to that. We're going to talk about all of that stuff in more detail because there's some terminology and definitions tomorrow, okay? There is another way that hydrogens can be non-equivalent. It's also a three-dimensional effect. We're going to talk about it tomorrow. They can be not magnetically equivalent. This is generally called chemical equivalence. Okay? So tomorrow we're going to talk about magnetic equivalence, and we're going to talk about also stereoisomer non-equivalence, like if the two things are diastereomers. Okay? All right, so let me show you an example of this. Okay, or some examples, just really quickly. Okay, so this is the kind of really simple question in this area, but then, well, just like, you know, when we did, are these two things identical, but then we use that as part of other problem solving, we're going to have more complex ones, okay? So are these chemically equivalent? So what we're going to do is we're going to do what's called the substitution test. We're going to replace each with some imaginary group or atom X. Okay, so here we go. Right, so I replaced hydrogen 1 with X. Now I replace hydrogen 2 with X. Okay, and then what I do is I ask, what is the relationship? And again, that's a skill that we worked on in first semester lecture class. And by now, I'm sure you can look at them and just say that these are clearly identical structures. And so what we would say is they're identical. So hydrogen 1 is equivalent to hydrogen 2. I'll be honest with you. This is sort of the long way. You could have probably done that in your head. If you can do it in your head, do it in your head. But if you're having problems, this is the long way to work it out. In most cases, the 3 hydrogens of a single methyl group are equivalent. I'm gonna do a really simple example, guys. Okay, so notice that this is basically a methyl, right? It's a CH3. So if we do our substitution, since we're comparing all 3 hydrogens, we have to do 3 substitutions. And then we ask the same question, relationship. These are all identical structures, right? What that means is we don't usually have to do these methyl group equivalent substitutions, right? We can just look at a methyl group and say, at least those are all equivalent. Okay. A group of equivalent atoms, what we're going to call them is a unique set of equivalent atoms. The idea being that they're unique, which makes them different from other sets of equivalent atoms, right? So like if I had a CH3, those are one set of equivalent atoms. Then if I have a CH2 that the 2 are equivalent, that would be a different set. And so that's why each one is a unique set, right? So that we can say there's, how many are there, right? So what organic chemists do when they do unique sets of equivalent atoms, I'm going to show you some of these here, okay? I'll show you an example with a little bit more complex molecule, okay? We want to find each unique set of equivalent atoms, right? And then we want to mark them so that we can count up how many total different unique sets there are. So what we do is they assign a lowercase letter. So for example, we said that in most cases, pretty much all the cases we can think of, hydrogens that are all on a single methyl group are going to be equivalent to each other. So we'll call these 3 hydrogens unique set A. Those are going to be different from the CH2 hydrogens, right? So that's a second unique set. So we'll call that B. Okay, now I want you to watch this. This is kind of interesting. So now we have our aromatic ring. Do you see? It turns out you can prove this. If you were to substitute this hydrogen or you were to substitute that hydrogen, those would create identical structures because you could just take the molecule and go like that. So this and that are actually equivalent to each other. Similarly, this and that are equivalent to each other. And then this is different. So that molecule has 5 unique sets of equivalent hydrogens. So now imagine there's 2 test questions or questions, right, that I can ask you about this. And this is what I was talking about, how like on the MCAT or something, okay? So the first question would be, how many unique sets of equivalent hydrogens, right? Just how many? It's a number, 1, 2, 3, 4. In this case, it's 5. The second question would be, here's a structure, indicate each unique set of equivalent hydrogens by assigning them a letter. So in other words, I give you a picture and you have to write the letters on. Again, that's basically the level, that I would expect to see on an MCAT question for this, but we're going to use this later on, okay?
Professor, if we were to add a methyl group to anywhere in the ring, it's going to change the whole unique sets, right?
Exactly.
Can we add a methyl group and then see how it's going to be changed?
Absolutely. Let me do that real quickly. So I'm going to do this really quickly. There'd be A, there'd be B, and this, it doesn't really matter the order, right? That would be C, right? Because the two methyls themselves are not identical. Then we have these other hydrogens. Well, this one is clearly different from all the rest, right? And now we have this one, it's next to the ethyl and far away from the methyl. This one is next to the methyl and far away from the ethyl. So we get that. Now, I do want to also make a comment about these. NMR instruments have there's different strength ones, and we're going to talk about that again tomorrow, okay? The strength of an NMR instrument. The ones that are weak, the peaks are really fat. And so when you have two that are close together, they sort of broaden into a blob. Does that make sense? So that you can have a situation where like two signals look just like one really fat one, okay? So what we see is these hydrogens on the benzene ring that I've labeled C, D, E, or E, F, G, A, okay? Often in a weak NMR, we're not going to see a separate signal for each. They're going to kind of be blobbed together. But in a powerful NMR, and this is one of the advantages of a powerful NMR, in a powerful NMR, the signals become thinner and thinner and thinner. So what happens is the blob separates, and we can literally see each one.